G'day everyone again, and welcome back to the Linear Relationships and Algebra series on my channel. Today we are going to look at some stuff around inequalities, this time looking at regions on the Cartesian plane. So this is a bit more of an advanced topic for Year 10 5.3. So if you're not following, that's okay, but if you can follow, that would be fantastic. So we have a previous video on inequalities that talks about how inequalities work on the number line, and you can see there I've got an example of a number line. Alright, so that's just a straight number line. And you can see a couple of things about it. We can see that this is actually representing the x is greater than minus 2.5 solution. And here's our minus 2.5. And you can see there that it is an open circle. Okay, it's open. And that indicates that it's not equal. So it indicates or is indicating not equal to. You can also see on that number line that the arrow is pointing or traveling in the direction of possible values. All right, and that's how these things work on our number line here. When we move to the Cartesian plane, so we expand our number line into a plane, we can now shade in regions. We now have regions, whole areas of that plane that can potentially satisfy the inequality. And this is how they're drawn up. For example, we have the solid line here. So if you remember that the coloured in dot meant that it could be equal to. Alright. So this solid line will indicate that as well. And then we've shaded in underneath to show that yes, all those points will satisfy our inequality. Anything in that blue shaded spot will satisfy from the line down. Okay, the solution to a bivariate inequality, so one with two variables, is shown by shading that region. Okay, and it can be called a half plane. Okay, sometimes called a half plane. Now there are some rules for drawing up inequalities. Let's have a look at them now. Okay, our first one here. Okay, this first one is y is greater than or equal to mx plus b. So we're just going to use the generic version of the equation. All right, so this is a greater than or equal to. So you'll notice that it has a solid line to indicate potential equality, and the shading is above the line, all right, because it's greater than. Okay, so the shading says that those values above the line or greater than that line can satisfy. Our next one here, well, this one is just the y is greater than mx plus b. So it's a dotted line now, indicating that it does not equal the points on that line. Alright, so solid line can be equal, dotted line cannot be equal. And again, we are shading above the line. Above the line to represent that those values can satisfy that inequality. The next one along, I'm sure you can probably guess this one is y is less than or equal to mx plus b. You should have been able to guess the equal to part because it is a solid line. Okay, and the shading is underneath now. The shading is below for the less than. Okay, so shading above for greater than, shading below for less than. And our last equation here, or inequality, y is less than mx plus b, indicated by the dotted line. And again, shading is below. Okay, so they're the rules. They're essentially what you need to be doing. You can draw up your inequalities just like you would any old equation on the number plane and then go from there. What happens though if our inequality doesn't look like y equals mx plus b? Glad you asked. It might look a little bit like this. As ax plus by equals d. Now, this is not the same as the other one, but you can use another test. So you can also include any inequality sign in this particular type of equation. We actually have a bit of a test we can do for these ones, and that is testing the point at the origin. So that's testing 0, 0. All right. We can test the origin, or 0, 0, to find out which side of the equation it sits. Now, it's pretty easy to see in this example, because I have the drawing there, that it would be on the underside. Okay. We now can look at this and we can actually work it out, right? We can see that we've got the equation 3x plus y equals 6. That's our equation, 3x plus y equals 6. It's been drawn there. We can test that point 0, 0 by substituting in 0 for the x and the y. So that becomes 3 times 0 plus 0 equals 6. Well, that's actually going to be less than 6. So I'm going to erase that equal sign, and I'm going to change it to a less than sign. So that means that that point of the origin is below, or in the region below the line. Okay, that's the test for what we're looking at. You might want that to be in the region. You might want it to not be in the region. It depends on what your problem is and how it's being presented to you as to what you need to do for it. Next, we have multiple regions. So this is when we get two inequalities or more put together. Okay. All right, so multiple regions. So this is for two or more inequalities. Okay. You'll have the shaded regions. The shaded regions on the number plane. Alright, as shown in our diagram there. What happens is they overlap. The regions will overlap. Alright, and then this overlap will form an intersecting region. Okay, so intersecting a region, and the actual point of intersection for that intersection will be the solution to the simultaneous equations or inequalities. Okay, that's what we're going to be doing with two or more inequalities on the same number plane. So only where those bits overlap need to be shaded, as you can see in that diagram, because that's the intersecting region. We don't need the rest of it. And that point of intersection will be the solution. Now, if it's an open dot, that intersection will be where things don't equal and everything else will satisfy. Okay. Last little point though. For definition and clarity in all of your diagrams, and you should always be doing your diagrams. You should label all features. So you can see there we've got the intersecting region labeled. We have the point of intersection labeled. We even have the origin and the x and the y axis labeled. So that is the base knowledge that you need to be able to work with regions on the Cartesian plane. In the next video, we're going to smash out some examples. I'll see you there.